We are the Flying Revolutionaries of the George Washington University, and this is our 2020-2021 DBF submission for the Cirrus aircraft. Here's an overview of the presentation where we explain how Cirrus is the best aircraft to meet the competition requirements. First, we will discuss the team's process. The requirements were studied in detail using methods like House of Quality. In previous years, the team had not been able to create a flight-worthy plane, so we decided to develop a stable, reliable, and simple aircraft that has high endurance to complete the delivery and sensor missions. The team utilized an iterative design, manufacturing, and testing process that was driven by the requirements. In these phases, the team only focused on objectives that improved the mission performance of the aircraft or better met the requirements. Trade studies were conducted on the control surface sizings and locations to optimize for stability and control authority. CFD studies determined that our selected aileron size provided enough rolling moment to control the aircraft. The aileron placement, along with reflexed ailerons, decreased the chance of wingtip stall, a vital consideration for the high wing loading of our design. The tail control surfaces also provided adequate pitch and yaw to mitigate the adverse aerodynamic effects of the deployed sensor. When sizing the stabilizers, the tail volume coefficient values were used as a reference for the aircraft's stability, and the detailed design stabilizers had coefficients within standard target values. Another trade study compared 3 wing rib cutout designs to determine which was optimal for the aircraft. Finite element analyses were used to determine the strength and weight of each design. The maximum expected stress was well within safety limits, and therefore the third design was selected as it had the lowest weight. Next, we will discuss our sensor fin selection. A critical requirement of the sensor is that it remained aerodynamically stable during flight, otherwise the pilot could lose control of the aircraft. We used a car with a bicycle rack to test various sensor fin designs at high speeds, and an IMU to record sensor position during the test. Out of the 4 designs tested, the dihedral performed the best and was selected. Here is an overview of the final detailed design. The final 3-view drawing and key dimensions are shown here. Next, we will discuss the gross weight of the final design. Less weight means the aircraft will have a higher thrust-to-weight ratio and more endurance, all of which is important while towing the sensor. We initially over-designed the aircraft structure, resulting in an expected 17 pounds weight, so we iteratively reduced weight to 12 pounds for the final design. Since the aircraft was lighter than expected, we were able to carry more shipping containers for the delivery flight, which increased our mission performance. Additionally, tail weight was also reduced so that the final aircraft had a favorable CG between 25 to 30% mean aerodynamic chord for all missions. Next, we will discuss the final control architecture. The sensor and winch system were designed with simplicity in mind. These components were plugged directly into the receiver and can be activated with switches on a transmitter. The sensor deployment mechanism and sensor electronics are shown on the right. The report documented Arduinos and a cargo door in the detailed design, however these were removed from the final design to favor simplicity. Next, we will discuss the propulsion system. For the staging and delivery flight, a single 6,000 mAh battery was used. For the sensor flight, 2 batteries were used, which resulted in a maximum flight time of 14 minutes with the sensor deployed. This exceeded the endurance requirement and provided ample safety margin for the pilot to land. For the staging flight, an 18x10E propeller was used. For the delivery flight, a 16x12E propeller was used, and this increased the speed of the plane, improving performance on the delivery mission. Next, we will discuss the performance results of the aircraft. The actual lap time for the staging flight was 40% faster than predicted. The delivery flight performance was better than predicted, and the total number of laps on the sensor flight was around 40% greater than predicted. Performance increases were likely due to the increase in thrust-to-weight ratio after the weight reduction and focusing on the requirements throughout the entire design and build process. Overall, Dolly functioned well, exhibited high flight reliability, met or exceeded all mission requirements, and, per the test pilot, handled very well and had ample thrust. For all of these reasons, we think she is the best aircraft to meet all of the mission requirements. And finally, we would like to acknowledge and thank everyone who supported the team this year.
All right, welcome to the technical inspection. This is the technical inspection video for the Flying Revolutionaries of the George Washington University. So here is our aircraft, which is our second aircraft named Dolly Parton. And here's just an isometric view of the aircraft. So go to the wing. We have a chord length of about 12 inches, wingspan of 60 inches. And show the ailerons rotating. Okay. move to the back of the aircraft now. So here's our tail. Same as listed in the report. All the dimensions are the same. Okay. Right. And here is the interior. So you can see right here the L brackets that we described in the report, aluminum. We have our battery basket here, which holds a battery. This did change slightly from the original design that was submitted in the report, but it's essentially the same. We have our formers here that are made of balsa. And our cargo for mission 2 is going to be stored in here. We'd actually have to remove this sensor, but that's pretty easy to do. It's just zip tied in there, or excuse me, the sensor deployment mechanism. Okay. And then we're going to show you how the winch and the sensor work. So with the switch of a button on the transmitter, I can deploy this. And we'll bring it out to about 50 inches, which is 10 times the length of the longest diameter on the sensor. Okay. And then you can see the sensor lights up like that in a unique pattern. We have 6 lights on here. I'll turn it off for now. And then retracting it. So retraction is pretty smooth, and it pops right into the sensor docking station. Just like that. All right, thanks for watching the technical inspection. Okay, here's a demonstration of Dolly Parton taking off. Dolly gets up to takeoff speed and pulls off the ground gently, well within the 100-foot requirement, and then she banks to the right. And here's a sample of Dolly Parton coming in for a landing and touching down. So she's approaching from the right. Wind speeds were a little high during this test, so she had to come in pretty fast because she doesn't have flaps. But she touches down smoothly and comes to a complete stop. No issues with the landing gear or with anything on the aircraft. And here's a demonstration of the sensor deployment. So the sensor pops right out of the aircraft, and the winch system deploys it to 50 inches, which is the length requirement. And as it's still deploying right now, but as it comes around, you'll be able to see the sensor with its 6 lights in a unique pattern. It is a bit hard to see the lights in this video due to the video quality, but they were visible at the field during the test. And the sensor stays within a 30-degree cone the entire time it's deployed, so it's aerodynamically stable. And the aircraft is also aerodynamically stable. It's actually, the pilot said it was more aerodynamically stable with the sensor deployed than without, likely due to the increase in drag, but you can see that right here. And finally, I'm going to show you a video of the retraction. So the aircraft is going to come around and start retracting the sensor, and you'll see the sensor pop right into the tail cone. Very smooth, no issues here. And thank you for watching.